Welcome AP Physics 1 students. This is the third video in which we're going to analyze the information and data you collected from the circuit's activity. Here we'll be focusing on the parallel connection. So in your handwritten notes, go ahead and draw the circuit diagram. You notice this is the same circuit diagram or schematic as in your circuit's activity. I just removed all of the ammeters. Make sure you draw the circuit diagram large enough because you know we'll be labeling things up. First, how do we know it's in a parallel connection? Well, you should be able to recognize that the resistors are independently connected. You should be able to see that if you take the 5 ohm resistor out, the 10 ohm still has a way to be connected to the battery. If you take the 10 ohm resistor out, the 5 ohm is still connected to the battery. They are independent of each other. From a physical standpoint, you should recognize that there is a junction there, where the wires are joined together. Anytime you see a junction, at the very least you're looking at a parallel connection. And then we're going to label up our circuit. We'll call delta VB the battery voltage, R1 is the 5 ohm, and R2 is the 10 ohm resistor, just like before. And now we start to look for patterns. First I want you to look at your voltages. Look at delta VB, delta V5, and delta V10. It should be pretty obvious that delta VB is about the same as delta V1 and the same as delta V2. And if you look at the big picture, they're pretty much all the same number. There are going to be some minor differences to be sure. We'll talk about those. Now, why would the voltages be the same? Well, let's track an individual proton. It starts here at the negative terminal, that's the bottom of the mountain, and then the skier takes the ski lift to the top of the mountain. Let's say it gains 5 volts, comes around here to the junction, and the proton has a choice. It can go down one path or the other. An individual skier with this choice certainly could not split themselves in two and go down two paths at the same time. It doesn't make any sense. So an individual proton that has gained 5 volts to the battery then might go down this path through the 5 ohm resistor and end up here at the negative terminal, which is the bottom of the mountain. On a separate run, gaining 5 volts to the battery, this individual proton might take the other path, going through the 10 ohm resistor and coming back to the negative terminal, which is the bottom of the mountain. And so no matter what, an individual proton that gains 5 volts to the battery will have to lose 5 volts here, coming back to start, or lose 5 volts there, but it can't go down both paths at the same time. This leads us to the idea again that the gains have to equal the losses. And so an individual proton that gains 5 volts has to lose it either through this path or this path. And considering there's only one resistor in each path, each one has the same voltage drop as is the voltage gain through the battery. Why are they off by a little bit? Well, it's the same idea we've seen so many times before, that every time there's a wire, it offers a little bit of resistance, and from delta V equals IR, whenever there's a resistance, there is a voltage drop as well. Let's now look at the currents. You might notice that the current through R1 is twice the current through R2. Let's label these on the diagram. We'll call I1 the current through R1, I2 the current through R2, and I total is the total current coming out of the battery. Now I1 seems to be about twice I2. Why would that happen? Well, the individual charge that gets to the top here has choices to make. Either take the low resistance path or the high resistance path. If you imagine 3 charges, which would be 3 skiers coming to the top of the mountain, when they see these choices, they might want to take one path or the other. This goes to the idea of resistance being like the difficulty of the slope. We've got the bunny slope, the 5 ohm path, and the black diamond, the 10 ohm path, and which slope always is more crowded? Well, of course, it's going to be the bunny slope. And so we'll go in a ratio of 2 to 1, which is the inverse of the ratios here. Twice as many charges will go down the easier path, half as many charges will go down the more difficult path, or in general, we can say that charges, just like people, tend to take the path of least resistance. Charges don't actually make a decision, it's just that the 5 ohm path has a more strong field down it, and the 10 ohm path has a weaker field, pulling fewer charges down its path. But you can sort of pretend it's like the skiers getting to the top of the mountain making these decisions, because they make decisions just like people would in any sort of situation, usually taking the path of least resistance. Now, I'm sure you know some people in your life who always take the path of more resistance. They might justify it by saying it's a challenge. They like to rise to that challenge. Or maybe they're just the sort of people who tend to make their lives more difficult for themselves by taking more steps than they need to. In fact, maybe this is you. Maybe you need to make some better life decisions, and you always take the path of higher resistance. But in general, you like to take the path of least resistance. That will help you understand what's happening here. Let's continue to look at patterns in the currents. Hopefully you notice that I total seems to be the summation of I1 and I2, and here you really don't have to make any estimations or look at the big picture. It should be pretty much exact with minor fluctuations in the meters. Why is this the case, that I total equals I1 plus I2? Well, again, let's watch those 3 skiers. The 3 skiers get to the top of the mountain. and they have a choice to make. They're going to go in a ratio of 2 to 1, which is the inverse of the ratio of the resistances. And so 2 of them will take the 5 ohm path and 1 will take the 10 ohm path. But no matter what, if 3 skiers went to the top of the mountain, 3 skiers better come down the mountain. This again is conservation of charge. If instead they didn't come down, we'd have lost charges. And of course this is where the bears get involved that we talked about before. And of course then the owner of the ski resort would get sued. But no matter what, the total current, it splits at the junction, comes back together at the other junction. The currents have to add back up to the total current. We cannot lose charges. Continuing to look at the patterns, we should be able to see that delta V1 equals I1 R1 and delta V2 equals I2 R2. This is most easily seen for the 10 ohm resistor. If you look at delta V10, it should be about 10 times the current through the 10 ohm resistor, I10. Might use a calculator to see the relationship of the 5 ohm resistor, but the point is that again Ohm's law works for the individual resistors, and now we're going to play a similar game, but this time replacing the currents with their relationships rearranged. And so I1 would be delta V1 over R1, and I2 would be delta V2 over R2. The left-hand side is I total, so we're going to replace it, you guessed it, with delta VB over REQ, always replacing the current with a voltage over resistance term. You should probably know what comes next. We're going to look for something that's common, and here we see that all the voltages are the same, so the voltages will cancel out. And what are we left with? 1 over REQ equals 1 over R1 plus 1 over R2 and so on and so forth, which will box in as our equation that will get us the equivalent resistance in a parallel connection of resistors. Just like we had done for the series connection, I want you to very quickly calculate what REQ should have been for the 5 and 10 ohm resistors. And so theoretically we should be getting an equivalent resistance of 3.33 ohms. Now you can do a similar thing, use that last column of your data chart, title it REQ, and we know REQ, the equivalent resistance, uses battery voltage and total current, and so for a few of the lines of data, you can do all of them if you want, but just a few should be fine. Go ahead and calculate what REQ actually was. Make sure you're using battery voltage and total current. Our theoretical equivalent resistance was 3.33 ohms, and more than likely you're getting things around 3.6 ohms, 3.7 ohms. It might go up to 4 ohms, maybe even up to 4.5 ohms, but they're similar to our expected 3.33. Notice each time, though, it's always more resistance experimentally than it should have been theoretically. And where's the extra resistance come from? Of course, we know it's in the wires. It's inescapable. The last part of this was to switch the order or position of the resistors by switching the 5 and 10 ohm resistors. Hopefully you noticed that really nothing changed. The total current should not have changed, and the resistors took their currents with them. Where whatever current was here with the 10 ohm moved over to here, and whatever current was here with the 5 ohm moved over here, where again, the position of the resistors does not matter. You could have swapped them and gotten the exact same results. And this concludes our analysis from the circuit's activity.